So in 10.2, we talked about arithmetic sequences in series. Now we're going to talk about geometric sequences in series. So um, a geometric sequence, basically instead of adding a number or subtracting a number every time, we're going to multiply a number by each time. So the amount that we multiply each time is called the common ratio. And again, I think it's going to be, once we get to our first example, it'll make a little bit more sense. The graph of a geometric sequence with a positive common ratio other than 1 is an exponential function. Whose domain is the set of positive integers. The common ratio is found by dividing the second term by the first term. And you could, this is true, I could take the next term divided by the previous term. I could do that anywhere. It doesn't have to be the second over the first, but it could be the 11th over the 10th. It would still be the same. All right, so write the first 6 terms of a geometric sequence where the first term is 12 and the common ratio is 1/2. So I'm just going to have 12 as my first term, and then I'm going to multiply by 1/2 each time. So multiply by 1/2, I get 6, 3, 3/2, 3/4, 3/8. And those are my first 6 terms. So I just keep on multiplying by r, the common ratio r. So looking at this, if we fill in this table, a1r cubed, and that's for a4. a5 is going to be a1 times r to the 4th. a6 is going to be a1 r to the 5th. So what's an going to be? a1 times r to the n minus 1. So the nth term is basically that formula right there. So an is a1 r to the n minus 1. So let's find the 7th term of the geometric sequence whose first term is 5 and whose common ratio is -3. This is going to be a7 is equal to 5 times -3, and then we want to find the 7th term, so 7 minus 1 is 6. So 5 times -3 to the 6th. So 3, 9, 27, 81, 243, 729. So -729 times 5. 3645, I think. -3645. I should check my math there. Okay, excellent. So we end up with that as our answer. Geometric population. So the table shows the population in the United States in 2000 and 2010, with estimates given by the Census Bureau for 2001 through 2009. Show that the population is increasing geometrically. So there's a couple different ways we could kind of think about this. But what we could do is if we wanted to take, say, from 2001, divide and take our number from 2000. So, again, this is A1, A2, etc. So I could take A2 divided by A1, 284 divided by 281.4. And so I get, it looks like I multiply by 1.009. So let's see what happens if I multiply 284. If I multiply 284 by that number, I should get approximately 286.6. So let's see what happens. And then what do you know? I get 286.6. And again, so and if we continue on, we'd see that that's the pattern. So R is equal to approximately 1.009. And again, we could just carry that through. Write the general term for the geometric sequence modeling the population of the United States in millions of n years after 1999. So again, we've got A1 is equal to 281.4. We got what R is. So AN would equal 281.4 times 1.009 to the n minus 1. project the U.S. population in millions for the year 2020. So again, in 2020, that is 21 years after 1999. So I'm going to have A21 is equal to 281.4 times 1.009 to the 20th, 21 minus 1, right? And we could even do it a little bit more accurately, right? We could go back and do this guy to the 20th times 281.4. And we get about 338.2. And again, yeah, I mean, I don't really round it or not. I'm not that picky. So that's million people. All right, so the sum of the first n terms of a geometric sequence. So, and this is true for any sequence, really. It doesn't have to be geometric. We call it the nth partial sum. So the sum Sn of the first n terms of a geometric sequence is in which, that should be an n. A1 is the first term and R is the common ratio is given by, well, let's come up with this formula ourselves again, just like on the last one. So if we look at the nth partial sum, you'll agree that it's A1 plus A1R plus A1R squared plus dot 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 plus A1 R to the n, that's an R to the n minus 2 plus A1 R to the n minus 1. That would be our, our nth partial sum. So hopefully you see where this n minus 2 comes from, right? I'm multiplying one less time than I am in the last term. And the reason for that is, let's multiply that by r, and let's see what happens. So I get A1R plus A1R squared plus A1R cubed plus dot 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 plus A1 R n minus 1, right? We're just adding 1 to that exponent. And then A1 R to the n. Now let's go ahead and subtract these. Notice what's going to happen. A1R minus A1R. A1R squared minus A1R squared. Again, it's hidden in here, but A1R cubed, all right, that's going to subtract. And so everything's going to subtract and cancel each other, except the only thing that's going to be left are A1 and A1R to the n. So on the left side, I've got Sn minus R times S of n equals, and then on the right side, I got A1 plus A1R to the n. Now let's factor an Sn out of both of these terms on the left side, and let's factor an A1 out of both of these terms on the right side. And so now let's solve for Sn by dividing by 1 minus r. So we get A1 times 1 plus r to the n over 1 minus r. And there's our formula. A1 times 1 plus r to the n over 1 minus r. Again, you're never going to have to prove that or anything, but it's just kind of nifty. It falls in your lap pretty easily. And then last question here is, before we move on here, what if r equals 1? Then I'm going to multiply by 1, so it's going to be 1a1, and it's going to be 1 squared a1. And this is going to be a1, a1, etc. So the sum of the first n terms of the sequence is just going to be n times a1. So I guess this is just showing it again. This is a1 plus a1 plus a1 plus a1. And we have n of them, so it's n times a1. Find the sum of the first 9 terms of the geometric sequence 2, comma, negative 6, comma, 18, comma, negative 54. So to get from a1 to a2, we're multiplying by negative 3. So a1 equals 2, r equals negative 3. So sub 9. So the ninth partial sum is going to be 2 times 1 minus negative 3 to the ninth over 1 minus negative 3. So you can kind of see it gets big pretty quickly. So 2 times 1 plus 3 to the ninth. Right, the minus sign stays because it's an odd power, and then minus and negative turns to positive. Keep in mind, if it was 3 to the 10th, if that was the 10th partial sum, it would still be a minus sign. It's not like the minus can cancel inside there. Just so we're clear, and then 1 plus 3 gives me 4. So I get 9842. And again, if you wanted to, you could just double check. You know, you might not believe me. So I could go from 1 to 9 of 2 times negative 3 to the n minus 1, or I minus 1, or t in this case because my calculator's still in parametric form, and I get 9842. So if we want to evaluate this summation, again, we need to figure out what A1 is. A1, plug in I equals 1. 2 times 3 to the first is 6. R, and we're multiplying by 3 each time, so R equals 3. So it's going to be the eighth partial sum. It's going to be, so 6 times 1. Again, it's 3 to the eighth over 1 minus 3. So 6 times 1 minus 3 to the eighth divided by negative 2. I get 19,680. A job pays a salary of $30,000 the first year. During the next 29 years, the salary increases by 6% each year. What is the total lifetime salary over the 30-year period? So again, if we look at this, A1 is equal to 30,000. R is going to equal 1.06 because each time we're going to multiply our previous salary by 1.06 to get our new salary. And we're basically going to find the 30-year period. So S30 is equal to 30,000 times 1 minus 1.06 to the 30th over 1 minus 1.06. So 30,000 times 1 minus 1.06 to the 30th divided by, and 1 minus 1.06 is negative 0.06, so let's save ourselves the trouble. And the lifetime salary in this case is 2.3, basically 2.4 million. Now you might say, wait a second, that seems way too big. But if you think about it, if it's 6% every year, in the last year this person is going to make 1.06 to the 30th, or sorry, to the 29th. In the last year, they're going to make $162,000 a year. So it seems a little bit more reasonable when you think of it about it that way. All right, so value of an annuity, this is kind of a complicated formula. I don't have it memorized. I'm not going to make you have it memorized. Let's see here. We had, it's right here. So this guy right here, P times 1 plus, so it's basically the same as our, I mean, I guess it's really not that bad to remember, but we basically have our 1 plus R over N to the NT, the same thing as our compound interest, but we have to subtract 1 and divide by R over N. So it's hard to know exactly what these blanks what it's supposed to be. So P times 1 plus R over N to the, and that there should be an extra parentheses there, to the NT. Make sure my R's and N's are distinct. Minus 1 over R over N. The value of the annuity. In this case, I'm actually going to skip the proof. I don't think it's all that enlightening. I think the other ones that we went through are kind of interesting, at least. So determining the value of an annuity. So at age 30, to save for retirement, you decide to deposit $100 at the end of each month into an IRA. So it's just stands for individual retirement account, but that pays 9.5% compounded monthly. How much will you have? How much will you have in the IRA when you retire at age 65? Find the interest. So basically, we just plug it in. So I guess I wasn't very clear about what was what up here. So P is the deposit made. So in this case, P is going to be 100. R is our interest rate, compounded N times per year. So here we have P equals 100. R is equal to 0.095. And then N is compounded monthly, so N equals 12. So I'm going to have 100 times 1 plus 0.095. Let me make that a little bit neater. 0.095 over 12 to the, again, we're doing it at age 30, so at age 65, that's 35 years later. So NT is 35 times 12 minus 1 over 0.095 over 12. So $100, and then it's up to you. We could make it pretty like this if you want, I guess. Oops. 100, and then let's do 1 plus 0.095 divided by 12 to the 35 times 12 minus 1 divided by 0.095 divided by 12. So I'll end up having about 333,946 and 30 cents. So 333,946.30. So that's A. Find the interest. So if we just want to find the interest, we're just going to subtract how much we paid in. We paid in $100, for 12 times a year for 35 years. So minus all of that. Oops, times 12 times 35. So our interest is, in this case, is the bulk of it, right? This is kind of the power of compound interest. 291 946.30. All right, a series is the infinite sum of an entire sequence with infinitely many terms. And sometimes the ones we're talking about here, we'll call an infinite geometric series, but they're not interchangeable. You can have series that are not infinite geometric series. So that's why I crossed out that little blank there. So basically it goes on forever, right? So the question here, how is this different from an nth partial sum? Well, the nth partial sum stops at a finite number. This means we keep adding until, over and over and over and over and over, and we never stop. All right. What's the infinite? If we could count on forever, if we could reach forever, what would the value be? And again, this is kind of, I kind of wish we were doing this in class, because this is kind of fun where you'll have interesting arguments about whether, like 0.9 repeating is 1 or things like that. But it's a lot of fun to ask some questions and debate about this. But for this, basically, we just got to say, if we were able to add up all the terms, what would it be? That's a little oversimplification, but that's really what we're doing. So if we're going to go ahead and do this, let's see here. If r is between -1 and 1, then the sum of the infinite geometric series is given by, well, basically, keep in mind, before we give that formula, keep in mind, remember, the nth partial sum was a1, 1 minus r to the n, 1 minus r. Now, if r is between -1 and 1, if I take a number that's absolute value is less than 1 and take a power of that, notice it's always going to get smaller. Like if r equals 0.9, then 0.9 squared is 0.81. And each time I multiply by 0.9, it's going to get smaller and smaller and smaller and smaller. So what ends up happening is this r to the n, as n gets really, really big, that goes to 0. So I end up with just a1 over 1 minus r. And if r is bigger than or equal to 1 or less than or equal to -1, then it does not have a sum. It just keeps getting bigger or it keeps getting smaller, larger in the negative direction. And it's, or you can even oscillate back and forth, but we call it a divergent series in that case. It does not have a sum. It does not converge. All right, so consider 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. If I go on forever like that, notice r in this case is 1/2. So a1 is also 1/2. So I get 1/2 over 1 minus 1/2. Well, that's equal to 1. So if I were to add up 1/2 plus 1/4 plus 1/8 plus 1/16 and so on forever, I would get 1. If I stop anywhere, I'm not going to get that. So notice, let's just do 1/2 plus 1/4 plus 1/8 plus 1/16. Let's just go a little bit, I don't know, let's maybe go to 256. Oh, I forgot to add. Wow, okay. Let's go back up here. So 0.399375 plus 1 over 32 plus 1 over 64 plus 1 over 128 plus 1 over 256. Notice if we look at this number, it's getting closer and closer and closer and closer to 1. Now you might say, well, at this rate, it looks like it's going to go above 1, but we could keep going on, for forever and ever and ever, and we would never exceed 1. And actually, we would actually never ever see, if we continue this process, we'd never actually see 1 here either. But you can kind of see we're getting closer and closer and closer and closer. We'll discuss this idea of getting closer and closer and closer to something next chapter when we start talking about calculus, our introduction to calculus chapter. But just basically what's going to happen is it's going to get closer. It's going to keep on adding 9s to the end here, and it's going to get closer and closer and closer to 1. And if we could figure out what the sum is, the sum is 1. All right, so find the sum of this number 8. Find the sum of this infinite geometric series. Again, a1 is equal to 3. R is, I can take the second term divided by the first term. It's -2/3. So I get the sum is equal to 3 over 1 minus a -2/3. So 3 over 5/3, which is equal to 9/5. So it's 1.8. And if you want to, add up a bunch of numbers, see what happens. You'll notice it bounces back and forth around 1.8. So it started at 3, and then the second partial sum would be at 1. Then the next one is at 2.3 repeating. It's going to bounce back and forth. All right, number 9. Express 0.9 repeating as a fraction in lowest terms. I always think this is kind of nifty. So, the question is 0.9 repeating equal to 1? Well, there's a couple different ways you can think about that. Remember, 1/3 is equal to 0.3 repeating. 2/3 is equal to 0.6 repeating. 0.3 repeating plus 0.6 repeating is 0.9 repeating. So, I'd have 3/3 is equal to 0.9 repeating, which is equal to 1. Well, another way we could do it is using this formula that we just had. Notice I can write this, so forget about that for a moment. I could write this as 0.9. Actually, let's do it in fractions. Well, here, it's probably easier to understand in decimal first, and then I'll write it as fractions just because it's a little bit easier to do the computation. So hopefully you'll agree that 0.9 repeating, I can just add a 9 in each spot and go on forever. So if I look at that, my first term is 9/10, and then notice to get from A1 to A2, I'm going to multiply by 1/10. So R is equal to 1/10. So S is equal to A1 over 1 minus R, which is 9/10 over 9/10, which is equal to 1. And this optional thing we are going to skip.